Hi, everybody. I just wanted to record another supplement here, this time for the solution to assignment one. So, well, we'll just get right into it. On the first problem was simply given an input-output relationship. Notice that the output depends on the sum of the input at different times. That makes it a linear system. And well, the first thing, find the impulse response, basically says, okay, impulse response is just what we get if the input is a delta. So you substitute a delta for the input x, and you get that, okay? And it basically would look like this. Make the note because we do and will refer to this, and you should know the term causal. So this is a causal filter because its response, basically depends on current and past values of the input. And of course, that makes sense in real time situations, although it's not absolutely required if we like record a signal and then do something with it where things are not happening in real time. We can have non-causal filters. So we will talk actually more about that later. Another way of thinking of causal, though, is that it doesn't respond to an event before the event happens, whereas a non-causal filter will actually somehow respond to the event before it happens on the time scale. Okay? So again, in real world time, everything's got to be causal. The unit step response, so this is similar to the example we had. And basically the idea is that, okay, the unit step, we're going to get a response to an impulse at 0, plus an impulse at 1, plus an impulse at 2, etc. And so we basically position this here at 0, 1, 2 for the response to the first delta function. And the delta function positioned at time 1 gives us that, and the third one, and so on and so on. And if you add those together, you will basically come up with something like this, where it will settle into a steady state, but it takes a little time to get there. And that's an indicator of a low pass filter. In fact, this is a low pass filter. And generally, when we have something where the impulse response is all positive, it is going to be a low pass filter generally. In order to generate other kinds of filters, the impulse response is probably going to have some kind of negative element. Now, a low pass filter could still have negative elements in the impulse response also. So it doesn't work both ways. But if everything's positive, it's going to be a low pass filter of some kind. Okay, and I go through how you would do it mathematically, but I'm not going to go over that. But it does work out, and of course it's a pain to write all of those symbols and terms. So that's number one. Number two always generates some, I don't know, some stress, we'll say, because people want to just plug into the integral and solve the problem. Of course, you've been trained to work a lot of problems that way, but I'm trying to get you to think about what things mean. And in this case, it's better to think about what everything means conceptually before trying to just plow through mathematically, okay? So the output at any given time is proportional to the integral of the last 2 hours of input. If you just use that, then you can more or less do things by inspection, right? So part A was a rectangular input. So, just like break it up into segments up to time t equals -2. There's nothing in the window of the system, right? The system, I mean, I've said this before, but this system basically has a 2-hour memory, right? So it looks at the input for the last 2 hours and it responds, forgotten it. Okay, has no influence on things. So we just see what's in, we just see what the input looks like within that 2-hour window and integrate the input within that space. And of course, I gave you some relatively easy signals to do that with. And so you just kind of take them piece by piece. And the result for the first one would look something like this, right? Basically, you have a period from -2 to time 0, where the 2-hour window is just getting into, and basically moving across the input. And so it's growing linearly. And then there's a time in the middle there where the 2-hour window is totally within the time of input, the light for the system. And then it exits basically the same way it came in a linear fashion. And so that's the result for number 1. Part B, you do the same kind of thing, but we have a shorter input pulse. And so we're going to see, something like this. But of course, that's a little bit different because of the shorter input. If we go to part C, we have a very short input pulse. And, as that input pulse becomes shorter and shorter and shorter, it looks more like a delta function to the input. So this is actually an approximation of the impulse response, as we will see. And basically, we would get something like this for the very narrow pulse because, only once that enters into the 2-hour window for most of that time, and then the input pulse is totally within that window. And so we get an output that looks like this. Part D, you could do the same thing, but it's easier if you just notice that that input was the sum of part A and 1/2 of part B. And so it's a linear system. You can take the input and break it into pieces, get the outputs for each of those, and then add them together. This is an example of case where there are a couple of different ways you could approach the problem, but I'm kind of hoping you'll do it the easiest way. Okay, and this will happen on other assignments and exams. The way I'm thinking that you should do it is the easy way, and sometimes people don't see the easy way. I mean, they go down a hard road that if they did it right could get them the right answer, but not the easiest way. That's fine. It's fine for you to do it the hard way if you get the right answer, but if you do it the hard way, there's a lot of places you could make a mistake. Okay, so here's an example of do it the easy way. See if you want to call it a trick, we'll call it a trick. But it's important to recognize that because it's a linear system, right? That's one of the key things about it being linear is we can take it apart into pieces and then put the pieces back together. Part E, and so this is the delta function input, right? We want the impulse response now, and so again, you could do it with the integral, but integrating with delta functions is a little funky, so we're not going to do that. Instead, we're going to use the fact that you integrate the last 2 hours, right? And so if that delta function is within our last 2 hours, we're going to get an output. Otherwise, we're not going to get anything. And so if you do that, and then for the time the delta function is within the window, you're getting a constant value, right? And so this would be the impulse response of the system. Okay, remember, impulse response is the response to putting an impulse into the system. And when we say impulse, another name for delta function is unit impulse. Okay, so, okay. All of these other outputs, by the way, are convolutions of the input with this function, but we didn't do it that way, right? We didn't try to sit down and do convolution. We sort of did, okay? But that's not the point, right? Some of the points are here in bold. Recognize what this system does, okay? It's a weighted sum or integral of the inputs at different times, and that's a description of all linear systems. The weighting function, which we also might call the convolution kernel or impulse response, is always the same if it's shift invariant. And then causality, if the current output depends only on past inputs, as this one does, then the system is causal. Okay, so those definitions, linear systems, shift invariant systems, causal systems, are all important to recognize because that's the language that we use in this field. Okay. Third one is a 3-point averaging system. So this one's not causal because it has a response at the impulse response has a response at t equals -1, t equals 1, t equals 0. It's actually symmetric about 0, which according to properties should give us an all real transform. Okay. And if we use the methods similar to what we used in class, basically linearity to break it up, delta transform of a delta function, shifting property, we end up with an e to the j omega and a conjugate pair with that, e to the negative j omega, which can combine into a cosine, right? That's a thing you should recognize. And so the response of this system is that which is all real, and we should have gotten that, okay? And so, you know, when we plot that out, we get basically a half cosine function. Remember, it only only uniquely goes up to pi because that's the highest frequency we can get in a discrete system. Again, we'll explain that, why that is later. But we'll go with that for now. So this is the property of that. It is a low pass filter, which again, we would have thought because the impulse response is all positive. Okay. So that's the kind of thing we should get on number 3. Now, number 4, this one you have to do a little more manipulation, okay, and play around with things and get them into forms that you can work with. The real and imaginary parts takes a little playing around, but basically we just substitute the Euler relation in for that, and then try to get everything, manipulate everything to get. You need an all real denominator, and then you can break up the numerator. So we get real and imaginary parts like this. We can get the phase response, which would look like that arctan function. Again, not a nice, simple result. And the magnitude response, which you could get by, squaring this and squaring that, adding them together, taking the square root, etc. But it's generally going to be easier to do it with the complex conjugate. So you can leave that in the e to the j omega form and form its complex conjugate, take the product of those guys, and the result is this. After you simplify, notice this is all real, right? The j's go away, and they should, because the magnitude should be all real. So should the magnitude squared, right? If you were calculating a magnitude squared and you ended up with some j's, you either made a mistake or you didn't simplify enough. So keep that in mind. The magnitude response would just be the square root of that, which doesn't really simplify any further. And plotting those out, we get, again, for a particular value, you may have chosen a different value. You get plots that look like this. Again, this is a discrete system, so we only go up to pi. Now, the cutoff frequency. So notice that one of the key things to note is that the peak value does occur at frequency 0, but it is not 1. It is 1 over the quantity 1 minus a squared. So the cutoff frequency will basically define this in this case because the peak is at 0. And so we set that up knowing this, and the previous result for the magnitude squared, okay, and those two should be equivalent, and then we just solve for omega c, which requires a bunch of manipulations, and you get something that's not pretty, okay, but it is the right answer. Okay, so in the example of A equals 0.6, this is about 0.52 radians. Notice this will be in radian frequency, radians per unit time. So that's about here, which, you know, again, we'll accept that as being approximately correct. Okay, remember it's 1/2 magnitude squared, or 1/√2 if you're just using magnitude. Okay, 3 dB kind of thing. Okay, so that's what we get there. And then finally, the MATLAB assignment, basically pretty simple because I gave you everything you're supposed to do. So we have 3 Gaussians. It's important to normalize them so that the area under them is equal, because that means that when we take the FFTs, 0 frequency will be equal. Okay, and we get a better comparison of the 3 that way. And the point here, of course, is to demonstrate that frequency time kind of opposite relationship, that the narrow one in green in the time domain is the wide one in the frequency domain, and so, and vice versa, with the red being wider here, narrower here. And remember, you know, there's a lot of different ways to look at these. One way of looking at this is, if this is narrow, it's going to need higher frequencies because it's going to need sinusoids that are basically smaller, right, of higher frequency. So something narrow here or quickly changing is going to need more high frequency elements than something that is wider and less quickly changing. Okay, that's again the practical interpretation of what this whole thing means. So we will make use of that, you know, frequently, right, in the future. So that concludes my discussion of the homework solution. Certainly, if you have any questions, let me know. You know, we might bring up 1 or 2 of these quickly in class, and certainly you can ask me at the beginning of class next time as well. Okay, signing off. We'll see you all in class.